Hi, this is Michelle Cullen, and this is a quick tutorial video for the Planet Designer Lab. This is for Astronomy 103 taught at Prince William Sound College in lovely Valdez, Alaska. So you're going to be doing a lab that helps you design a planet, and we're going to overview some of the parts that will help you be successful. So what I'll do is talk about how in astronomy we compare planets. We don't want to use a lot of very complicated numbers, so we're going to just keep things simple. Instead of talking about the number of kilometers from the sun to a planet, we'll just use it as an AU, or astronomical unit. Remember, that is 150 million kilometers, but we can just say that Mars is 1.52 AU. Your planet that you can design will be maybe 2 AU, which would be twice the distance from the sun to your planet as the Earth. We're also going to look at temperature because the distance from the sun is related to the temperature. And astronomy is a little more complicated in the sense that we don't use Celsius, we use a system, an absolute scale called Kelvin. But just to get a perspective, Celsius and Fahrenheit, which you're probably very familiar with Fahrenheit if you grew up in America. Fahrenheit is based on the human body. It's supposed to be 100 degrees as a human body, but that's wrong too. It's 98.6, or actually most people are 97. And so it has the boiling point of water at 212 degrees, as you can see over here, and 32 is a freezing. It's not a very nice system, so we're just going to get rid of Fahrenheit, and in science we use Celsius, which is actually beautiful. Celsius has water freezing at 0, and it has the water boiling at 100, and so we go up 1 degree Celsius to get between freezing and boiling at 1 atmospheric pressure. So Celsius is okay for things on Earth, but in space we have very extreme temperatures, so we'll use Kelvin. And Kelvin, the absolute scale, doesn't need a degree by it. 1K doesn't need a circle for degree. It's just a unit that we have 0 being absolute 0, which a lot of you may have learned absolute 0 is where all motion stops. But that's not really true. It's more about where an ideal gas, that it slows down as much as it's going to slow, and there's no more heat that can be dumped out of it. So 0 is as cold as we're going to get. And you think of space being very cold, but actually space is 2.7 Kelvin, which would be minus 270 Celsius. So it's cold, but it's not absolute 0. There's actually a little heat in space, very little. The beautiful thing about Kelvin is that it is the same unit going up 1 degree going up. Kelvin is 1 degree Celsius. So that makes it super easy to convert. So you just add 273.5 or subtract if you want to see how it is. So 273 degrees is where water freezes. There's still a lot of energy and heat in freezing water that you could take out and get it colder. Okay, so another way you may have been familiar with Kelvin is that in photography and in light bulbs that you may go by, they will have them in terms of Kelvin. And a lower, cooler light bulb is red. So red is 1,000 Kelvin. We go up into the whitish one, 5,000, and then really hot light bulbs emit a shorter wavelength are 10,000 K. So that's just a little information for you if you go to buy light bulbs and you want to get a warmer color that is, or not warmer, it's actually a redder color, which is actually cooler. That would be a lower temperature in your Kelvin. Okay, so let's keep going on for the lab. You're going to be asked to fill out a table, and you're going to look at the distance from the sun versus the temperature of these different worlds or planets. And I have some different links for you. You can just Google if you want to fill out this table. Here, I'll see if I can find the table. I'll go back into my switch over here. Sorry about that, I didn't have it prepped. The table is right here, distance and temperature in our solar system. So you're going to fill this out and do the best you can. It's pretty easy if you just go to this NASA link and there's a little thermometer. You can try to guess what that number is close enough, or you can look on this chart here. There's also the 9 Planets is a really nice website. Let's see. If you go to the 9 Planets, you can click on the planet part, which is over here. You could click on whichever planet you want. And they want to try to sell you things, but here's Mercury. You can click on the 8 planets. I don't know, they want to sell you things. Close. And you can compare. Mercury has a quick fact little data sheet here. You can get the range of the surface temperature, and you can also get the distance in AU, 0.39 AU. So we're going to go back to our lab, our explanation for our lab. The next part after you fill out your table on temperature is how big or small the different planets are in our solar system. And I call them worlds because we're looking at the moon, and sometimes I have you look at different smaller dwarf planets. So you can look at your Appendix F, which I just copied here, and this will tell you everything in terms of Earth, so we don't have to use lots of big numbers. We can look at the diameter of Mercury over here in terms of Earth diameter, but what I want you to look at is it in terms of mass. So it turns out that Mercury is 0.05 the mass of Earth, and then we can also look over here at the end at the surface gravity. And the gravity is related to the mass. Bigger planets have more gravity. So we'll look over here at Jupiter. Jupiter has a mass of 318 Earth mass, and it has a surface gravity of 2.5 times the surface gravity on Earth. And that would be if you were on the area that's kind of like sea level, or 1 atmosphere pressure of Jupiter would have a gravity of 2.5. Now gravity is also a little more complicated. Just briefly go over how gravity could be important to you. Do you remember, if you've ever had any other science classes, physical science, that the acceleration due to gravity on the surface of the Earth is 9.8 meters per second squared. But for simplicity, we'll just call that 1g. It's a relative standard again. 1. Earth is 1. Then we look at the how that Earth's gravity is proportional to the mass. So smaller planets have less gravities and smaller worlds. And I just wanted to quickly say too that the acceleration due to gravity is inversely proportional to the square of the distance. So as you get further away from the planet Earth and you leave it in a spaceship, you will experience inverse squared law. It will get less and less the further you go away. So when you leave the space Earth and go to the space station, it's really very, very close to the atmosphere. You actually get 0.89 G, almost 0.9 G. If you were, so why are the astronauts in the space station floating around if there's actually almost 1 g on, if you were just there. That would be if you were in a fixed, like if you put a ladder up to the space station and you were just there and you were spinning with the Earth right above a point. The reason why the people on Earth experience quote unquote 0 g, which I'm going to call microgravity, is because if you were there falling, they are orbiting the Earth and they are falling down towards it, but they miss it, and so they keep going around. And when you fall, like if you go in an airplane and it starts diving, you will experience microgravity. You will start floating because you're diving towards the Earth. That's exactly what the space station's doing. It's diving towards the Earth. Why doesn't it hit it? Because it's going fast enough that it misses, and it just keeps going around. It's going so fast. So anyway, gravity is important. Smaller worlds have less, larger worlds have more. And gravity, I want you to think about it. How would gravity affect the atmosphere? Well, if you have a lot of gravity, you could collect a lot of atmosphere easily. If you have none, it might get blown away by the solar wind. Cosmic rays could just blow your small light gases away, especially if they break them down into like little bits of oxygen and hydrogen. So that's one way you might not have an atmosphere or liquid water on a small, teeny tiny planet like Mercury or the moon that doesn't have an atmosphere. But here we have, there's this little picture shows there's liquid water on Europa and Titan. Well, it's underneath a frozen layer, so it's protected from the cosmic rays blowing it away. Okay, so don't think too much about it, but just know that if you're big or small, could affect your ability to have life and could affect your ability to have water. Well, the other very important concept for this lab and for astronomy is the concept of albedo. And albedo is simply reflectivity. So when you read about this in the lab, you could get confused, but it's simple. Reflectivity. The more you reflect, the higher your albedo. So snow and things that are white are very reflective, so they have a high albedo. Snow on this mountain up here is about 90% if it's white and clean. Dark soil or roads that get hot, when the sun hits it, you're walking barefoot in the summer on a hot road, it's because it has a low albedo and it's not reflecting the light, it's absorbing the energy from the light. So that's an important factor that you're going to plug into a formula, an app that you're going to use for your planet. And I could have had you do a lab where you had a light and you had 3 temperatures and you could actually measure the different albedo of different surfaces and see how that same amount of light will change the temperature of those different surfaces. There's an app that you could actually get, and if you have a standardized gray card, you can use your smartphone to take pictures of different colors and you could figure out what their albedo is, and that can be used to determine your temperature later on. So this is important on Earth because our polar ice caps have been melting and not replenishing over the last decades, and that changes the albedo of the polar cap. So when it's darker with a low albedo, it actually sets up a cycle that makes it warmer, just turning it dark, absorbing more heat from the sun, melting more ice. So this is a great video if you want to watch the annual Arctic sea ice minimum, and you can just see what's happening. But we digress. Let's go on to the next part that you're going to plug in, which is your greenhouse effect. And greenhouse effect is related to the atmospheric pressure. On Earth, we have a bubble of invisible gases around us that are thicker and have more pressure, lower towards the surface, and thin out as we get further away from the Earth. And so on Earth, you know, maybe when you're pumping up your tire that you use pounds per square inch. In metric, they use grams per square meter. But another universal measurement is called a bar. One atmosphere is 1 bar on Earth. And so a bar is, 1 atmosphere is actually 1.03 bars. So in general, we can say we live on an atmosphere of 1 bar. And different worlds with different atmospheres have different atmospheric pressures. So if you were on Mars, you know, intuitively, you've probably heard it has a very thin atmosphere. It only has 6 bars. That means if you had a meter cube you just got a meter of Earth's atmosphere on sort of the surface, it would have 1,000 grams per meter cube, which would be one bar, or 1,000 millibars. And on Earth, there would only be 3 grams in every meter cubed. So it is only going to have 6 to 10 millibars pressure. So, you know, 0.006. And so because the atmosphere is so thin, that's going to affect its greenhouse effect, and it's going to affect its temperature. Venus, on the other hand, was not on this chart, but it has a super thick atmosphere. It has so much atmosphere that it has 93,000 millibars, or 93 bars pressure. That is the same, that's the same as 3,000 feet below sea level on Earth. And so that means that it has a surface temperature on Venus of 740 K or 467 degrees Celsius. So there is a lot of heat and a lot of pressure. But it's not just the amount of molecules, it's the type of molecules that matter too. So as you've heard, there's a lot of carbon dioxide. 95% of Mars' atmosphere, well, there's not a lot of carbon dioxide because there's only 3 grams per meter squared. So even though of those 3 grams, 95% of that is carbon dioxide, it's still a little bit. But on Venus, it's almost all carbon dioxide. And there's so much of it that it makes it hot. Let's look at the next slide. The next slide shows the greenhouse effect, and it shows how the sun, visible light comes in, gets reflected back as infrared, as heat, and heat is trapped very simply. It's much more complicated than that, but that's the general idea. So if we compare the 3 different types of planets, worlds, we've got Venus, Earth, and Mars. We can see the relative pressure is a lot of pressure, 1 pressure, and very tiny little amount of surface pressure. And then we can see the greenhouse gases and the temperature. If there were no greenhouse gases, and then the actual temperature. So Venus, if there wasn't this carbon dioxide, if this was all nitrogen, not a greenhouse gas, it would actually be very cold, but it's not. It's very warm because it has so much carbon dioxide in it. Let's move on. The final factor you're going to put into your program at the end of your lab is the type of star or the mass of star. And so we live on an average star that's sort of friendly. It's a G-type star, and it is putting out just an average kind of Earth amount of light, and we are at this one astronomical unit away. So that puts us in a great spot for liquid water. But if you were to change the type of sun and make it a more massive sun, more massive suns put out more heat. And since they put out more heat, the habitable zone gets pushed further away if you were by a bigger star. Smaller stars put out less heat generally, and they could have habitable zones that are closer. So that's just something to consider, and normally that is the realm of star evolution and star mass. Will be next semester in Astronomy 104, which is going to be a cool class. But for now, for this lab, you just need to know if you were by a different, more massive star, and we just would do it in terms. If it was like 2 times the mass of our sun, 3 times the mass of our sun, 100 times the mass of our sun, you could see how that would affect the temperature on your planet that you're going to design. Okay, so the final part, once you've filled out all your tables, you're going to go and you're going to use the planet temperature calculator. And I don't know if I can actually get this in here. It's Screencast-O-Matic is not being super friendly here. Let's see if I can move it. You're going to use this temperature calculator, hit build, and you can go through and you'll click on the mass, click on the distance, click on the albedo, click on the greenhouse effect, and change these numbers, and then hit your summary, and it will give you, you can't really see it very well, but it will give you some numbers, and then hit your results, and it will tell you all about your results. So that is a not so quick overview of how to do the lab.